Today's video is going to be about finding the order of elements inside Sn. And it turns out that this is easy if we have a permutation that is written in disjoint cycle decomposition. In other words, what we're going to basically be doing is we're going to be letting alpha equal beta 1, beta 2, all the way up to beta k, where the beta i's are disjoint cycles. And what that means is that each j inside the set 1, 2, all the way up to n is moved by at most one of the betas. If j is actually fixed by alpha, in other words, if alpha of j is equal to j, then j won't appear in any of the betas. And it's important to realize that disjoint cycles commute. And the easiest way of seeing this is to actually just take two very basic disjoint cycles. We'll look at 1, 2, 3, and we'll look at 4, 5, and we will do them in both orders. And what we're going to do is we're going to look at their two-row notation. And in both of these, we have the same top row. Now, in this first one, we're going to start here and then go this way. And so in the first one, the way we would compute that into two-order notation is we would say 1 goes to 2, 2 goes to 3, and 3 goes back to 1, and then 4 goes to 5, and 5 goes to 4. In the second one, again, we're starting on the back side and going towards the left. And so we start by looking at 4 goes to 5 and 5 goes to 4, and then we proceed on to this permutation, and that still gives us 1 goes to 2, 2 goes to 3, and 3 goes back to 1. And these two things are the same, so they are equal. Well, so disjoint cycles commute. Well, that has some major implications for looking at powers of permutations that are written in disjoint as products of disjoint cycles. So if this is the disjoint cycles decomposition of alpha, so we know that the betas are all disjoint, then it turns out that if we look at alpha squared, that would just be one copy of the betas, followed by another copy of the betas. And we have parentheses. And it's important to realize that this is just one copy of alpha, and that's one copy of alpha. But when we also realize that the betas commute, we can rearrange this, and we're looking at beta 1 squared, beta 2 squared, and we continue all the way up to beta k squared. And this also generalizes. In general, if we look at alpha to the L, this is going to be beta 1 to the L, beta 2 to the L, and so on all the way to beta k to the L. And of course, the order of alpha is equal to L if and only if alpha to the L is equal to the identity permutation, and alpha to anything else, I'm going to call it alpha to the I, is not the identity permutation for I equal 1, 2, all the way up to L minus 1. In other words, L is the smallest power of alpha that is equal to E. Now, what I really want to do is I want to think in terms of E being equal to beta to the L, beta 1 to the L, beta 2 to the L, all the way up to beta k to the L. And we're doing this because we're assuming that the order of alpha is equal to L. Now, what this means is that beta 1 to the L is going to have to be E, beta 2 to the L is going to have to be E, a beta 3 to the L is going to have to be E, all the way down to beta k to the L is going to have to be E. And this is because no j inside the set 1, 2, all the way up to n is moved by more than one of the betas. Now, if I think about a single cycle, so we're going to look at beta sub, let's call it beta sub j. And beta sub j is going to be something that I'm going to call A1, and he's going to go to A2, and we wind up getting down to A something. And I don't know what this something is. And let's see. In the context of, well, I guess we can call this M, because in the context of our stuff, N is being driven by Sn, and K is the number of betas, and L is the order of alpha. And so, and I'm wanting to look at I's and J being in the set 1, 2, all the way up to N. So M is a convenient way of doing this. Now, if we start looking at this, it's pretty easy to realize that we can figure out beta to the j of A sub something, let's call this something I, and this is just going to be A to the I plus 1 reduce mod M, the length of the cycle. I guess that's the length of beta j. And beta j squared of AI is going to be, well, we jumped twice. So we're going to go from 1 to 2 and then to 3. And A2 is going to go from 2 to A3 to A4. And AM is going to go to A1 and then to A2. And so again, this is reduce that subscript mod M. And I guess I should say the subscript. So what this basically means is that beta j to the L is going to be, well, actually, I want to not look at beta j to the L as a cycle. I want to look at beta j to the L acting on one of those A's. That's going to be A to the I plus L by our previous work. But he's also got to be AI since beta j raised to the L has got to be E, and that's because the order of alpha is equal to L. And so what does this tell me? Well, this tells me that L has to be a multiple of m the length of beta j. And so what does this really mean? This says L is going to be a common multiple of all the lengths of all the betas inside alpha equal beta 1, beta 2, all the way down to beta k. Well, the first and smallest place where you can get a common multiple of all of them, so the smallest number that works is the least common multiple of the lengths of all the betas. Well, what this obviously means is that we need to have some decent notation for conveying such things. We've discovered that the order of a particular cycle is just its length. And what we're going to do is we're going to write beta sub j inside absolute values for the length of beta j. And that happens to also be the order of beta j. So what this means is that the order of alpha, which remember was L, is going to be the least common multiple of the length of B1, the length of beta 2, the length of beta 3, and so on all the way up to the length of beta k. Well, let's end with a quick little example. If alpha is something like 1 goes to 3, and 4 goes to 5, goes to 2, goes, let's just do that. And then we have 6 goes to 8, goes to 9, goes to 10. And this guy is living in, say, S10. Then we can look at this and we can realize that the order of alpha is the least common multiple of 2, 3, and 4, and that would mean that the order of alpha would be 12. And that will be enough for this video.